Hi guys, now we'll start with chapter 1, fundamental concept of chemistry. First of all, I will do it start with BIK, federal, and then we'll move to AKUB. First, I will cover all the topics of BIK, and then I will move to federal. And in federal board, I will do the topic that is not run in BIK. Now I will move to AKUB. AKUB has very few topics different than BIK and federal. So after BIK and federal, we don't really need to move to AKUB. But for some topics we will write. Now you will think that if you are BIK student or federal or just AQU, you may say this is over informative, but that is win-win for you actually, because you will only enrich in your knowledge. Also, this is helpful for your university tests and university admission tests. I will giving you the exam tips as well, buzzwords that will help you. Chapter 1, I will also do your numericals, each and every numerical that is in chapter 1 and any other chapter. Now first of all, I will go into BIK, and in BIK book the first topic is introduction to chemistry. Chemistry is a branch of science which deals the properties, composition and structure of matter, which is with the stages of matter which are governing these stages. But chemistry is not just that simple. It deals with spectrometry, fertilizers, how the fertilizer worked, how the computer is made, what are the things, what are the changes that occur forming a chemical compound, why through which the formation or transfer of electron, etc. So chemistry is simply what chemistry. So I can write chemistry is what chemists do, but in simpler terms we can write that chemistry is a branch of science that deals with the changes occurring in the composition of matter. Now you may now knew what is the concept of chemistry. Now the second topic is significant figures. Significant figures are those accurately known digits are significant figures. Now suppose I have a calculation, I am doing calculation on a scale of 6 inches that we usually use. Now if you can see the markings on it, the markings have inches defined, and then it's 10 markings in between. So the accurately known digit is just a marking, that is 0.1 inch 0.1 inch, that is. So that 0.1 is the accurately known digit, and that is a significant figure. 0.1 is the significant figure. Now how to determine the significant figure. Now we move to how to any non-zero digit in a calculation is significant. For example, I have this value. I have I have this value, 0.68. I have this value 0.6, that is 68. How many significant did have? So you can see now there is two number of significants there, because this is the non-zero digits and this is the 0, 1, and this is are insignificant. So but zeros may also become significant, but there are some cases. What are these cases? Now I'm going to tell you. If the 0 is present in between two digits, like if 0 was present in between this will make this 0 significant. Now this significant are 3 significant figures. Now there are three significant in this video, in this value or calculation or whatever it has. Or this, if zeros is on left of your calculation, that we already I have told you, that is insignificant. So only two significant figures are in this value. Now if the zeros are on right hand side of the value, will it be significant or not? It will be significant if there is a decimal in between. If there is a decimal, there is 4 significant figures. But if there is no decimal, there will be two significant figures. Also, significant figures are determine the accuracy of the instrument. If suppose that if the weight machine has calculate in order of hundreds, there will be two significant. But if it calculates in order of maybe you can say tens, in order of tens, so you can say there will be three significant figures. If the order of units, if it order units value, this value means that if it calculate 1, 2, 3, 4 kg like this, there will be 4 significant. So you can determine the 4 significant because the least count of the measuring instrument. Okay. Now the next topic is rounding off data. How to round off a data. So the rules are pretty simple. Rules of rounding of data are pretty simple. If value is greater than 5, is greater than 5, the value to left of it will increase. Like if it's 66.87, the value will become 6.9 if it's greater than 5. Now if the value is less than 5, the value is if less than 5, what will happen, that if the value is less than 5, the left of the the digit left to it will be retained. Like if it's 6.84, then it will be retained at 6.8. So I will round up to 6.8. Now what happens if it will be equal, value is equal to 5? If the digit left to it is uneven, like this, in this case it will be retained. Now if it not even, that if it was 6.7, if I say left figure was 7, the value will be not retained but increased by 1, that will become 6.8. So these are the rules of rounding off. Okay, now how we use our significant figures in addition and subtraction. Okay, whenever we add or subtract values of a calculation, like I have calculated a mass of two different things in two different weight machines. One has the least count of 0.1 and the other has the least count of 0.001. These two values. When I will add these two values, I will go for the least significant figure. now in this values, if in this value, if you can see that the we will no go for the least significant figure, but will we go for those which has the lesser number of digits after decimal. If it's for the multiplication point of view, we will go with the least significant number of figures overall. But in this case, when we will add something, like in this case, if we have to add it, we will go for the least significant value after decimal. Now we will go for the least. Also in this both calculation, two significants are present, but we'll go with the value that is has least significant figures after the decimal. That is this value. That is only one significance after the decimal. Now we will add it. That will become 7.61. The answer. But will for as far as the calculation we use in the significant figures, we will ignore this one and we will write as 7.6. We in a addition or subtraction, we will use the not number. We will not go with the number of significant. We will go with the least number of significant after the decimal. Now, if we multiply, what will happen? In the multiplication point of view, will not go with the number of significant after the decimal, but suppose the similar thing in kg, 0.8 kg multiplied by 0.81. Now in this case, there will multiply or dividing. We'll write the number of the least number. Now the least number of significants are 2, but okay. So we'll change the multiplication way bit, so it become what of it. Now there is a 3 significant figures and 2 significant figures. We have to write a calculation in this way, that is at 2 significant figures only. Now we have calculated out 6.8 multiplied by 0.813, and that will become 5.5284. But now we'll round off to 2 significant figures as we have calculated. Now we have to round off to 2 significant figures. Now we will round off to it to 4, 8. Now it's a lesser value than 5, so we'll retain the left number to the left. The value is greater. Now if we can remove that number, now 8 is greater than 5, so the 2 will become high, and that will become increased by 1, then become 5.53. Now we have to get 2 significant, but the 3 should also be removed. 3 is lesser number than 5, so the 5.5 will be the answer. So now you will understand how to add value with 2 different significant numbers and multiply or divide it. Use of exponents. Now we are moving how to use exponents. What are exponents? Exponents just you know that there in chemistry we deal with so low value of like for example the size of molecule. The size of molecule is way too in like in angstrom and nanometer. So that if we want to write it, it will become 0.0000. That will become inconvenient. So we use 10 exponents to some to write in a proper way. Now if we similarly we have a mass number of mole, there are Avogadro number of particles present. If we to write number of particles in 2 moles, that will become inconvenient if that 1204 and going on with the zeros. So we'll write in a exponential form. Now how to write in exponential form? Now if I have a value here, if I have a value as 0.03 and I have to write it in the exponential form, so it will become convenient for me now if I have to move the decimal towards the left, I have to uh, write the tens power in minus, because I am increasing this value, so ultimately I have to decrease value from here. Now, so if I am moving this decimal toward left, I will write 0.0003 multiplied by 10 raised to the power minus 1. Now this may become more inconvenient. Yes, I am writing more point of 0, so I will not write like this. This is an absurd form. So I will move this decimal to right, to 2 toward right. I have moved toward 2 right, so I will add 10 raised to plus 2, because I am increasing this value, so I will write in minus. Let me correct. In this case I have to increase the value. I did it wrong before. That I will write, if I have moved a decimal toward there, I will write 10 to the power 1 point positive. Now if you have to move this value right, I am increasing the number, so I have to write the exponent power in negative, and I will write 10 to the power minus 2 if the decimal was not there. But here the exponent will become 3 by 10 to the power minus 3. Now if I have a value 62400, now how I will write in exponential form? So the decimal is here, I will move toward 1, that will become 10 to the power 1. Now I will move toward this 10 to the power 2. Now I will move there to 10 to the power 3, 10 to the power 4. The decimal is here. This will value become 6.24 multiplied by 10 raised to the power 4. Now if we are using scientific notation, we are simply using log. What is log? In log there is we usually express, if you are using scientific notation, that will usually express the log into the power of tens. If the log is composed of 2 parts, and that is characteristic and mantissa. Characteristic can be either positive or negative, or mantissa will suppose the value this is 6300. You can find characteristic while looking the value of it. You can see that the value there will be at the value can be written as 6.3 multiplied by 10 raised to the power 3. Now so what will be the characteristic? The characteristic will be power of 10, and that will be this. That will be the characteristic. Okay, and that will be the mantissa, and this is the mantissa. That will be the decimal value is mantissa. The mantissa the value of mantissa can be found through log table, and if we want to have an idea of the log value of this value 6300, there is a simpler way. That if we have found this log 6300, there is a simple way how to find it. Suppose that we usually say that by this expression we can find out ay is equal to ax equal to y. That is y is the number, and a is a 10, and x is the log. This is the value of log, not log. This is the value of log. And now if we replace it by the values, that the power of x is unknown. The power of x is not the characteristic. Actually, it's the value of log. We can find out value of log like this. You can find like this. Now, if we move right y, we write the value of it 6300. Now you can see the value of 6300 lie between thousands to 10,000. That will be routed, it lie between it raised to the power 10 raised to the power 3 to 10 raised to the power 4. Okay, so the value of x will lie between 3 and 4. So that if it's true, the log will tell left calculator will answer in between. Now where is the mouse? Ion. Now we'll log 6. Oh, okay. uh 6300 log. The value is as set is in between the two values between 3 and 4. The value is always in between 3 and 4 if the value is in between 1000 and 2000. Now the value is come out to be, the log comes out to be, log 6300 comes out to be 3.8. So you can actually calculate log through your calculator or log table. You can use the both. If you don't have a log table, you can use this formula and you can calculate the value of log. And usually there is a log in each and every calculator, so you don't need it. In Casio calculator you can solve that equation, so you can solve this type linear equation as well. Now moving forward, the other topic is now the next topic is now error. What are error? Error arise due to several reasons. The two main reasons are classified as systematic and random. Systematic error is this error in systematic error, there are two types of error, that is systematic and random. Systematic error due to the faulty instrument, and random error due to random reasons. Actually, the difference of atmospheric pressure, the temperature, wind speed, moisture, etc. So to eliminate this, we have to eliminate systematic deviation, systematic error. We'll compare it with the instrument that is way correct. Also, we have to remove residual error in the apparatus. Now, as far as the random error is concerned, that random error we can solve the random error by taking the mean values of all the values. So you can actually solve the random error by taking a high number of values and taking its mean. So you will get a correct value. Now moving forward, in Kratchford book, the how to determine the empirical formula of a compound that is subjected to combustion analysis is given. So I will be doing that work formula, but doing the question number 8 that is given at the back of the chapter. That is, acetic acid contains carbon, hydrogen, and carbon. 4.24 gram of sample of acetic acid on complete combustion gave 6.21 gram of CO2 and 2.54 gram of H2O. Molecular mass of acetic acid is 60 atomic mass unit. We have to find the empirical formula and then the molecular formula. So first of all, we have to calculate the percentage of carbon. It's an easy way. Write mass of CO2 divided by mass of compound. That is the compound is that which is subjected to combustion analysis. I will writing it at COMP and then multiplied by atomic mass I will write it AMU of carbon divided by molecular mass of CO2. Now, the mass of CO2 produced is 6.21. We have to combine a percentage, so we have multiplied it by 100. 6.21 divided by 4.24, because that was the mass of the compound, multiplied by atomic mass of carbon is 12 and CO2 is 44. Now multiply this by 100. The answer is given is 1.46. Now 12 divided by 44. Answer is given 0.27. Now multiply 0.27 with 1.46 and then multiply it by 100. So the percentage of carbon is 39. 39.8. I am considering it as 40, rounding off. 40% is carbon. The organic compound is consisted of CHNO. So now we have to find out the percentage of hydrogen. To find out the percentage of hydrogen, we divide the mass of H2O produced with the mass of the compound and then multiply it by the atomic mass of hydrogen present in H2O divided by molecular mass of H2O. Now this is mass of H2O produced, that is produced, and molecular atomic mass of H, and this is H2O divided by 100 and percentage of H hydrogen. The mass of H2O produced is 2.54 gram. The mass of compound is 4.24. You multiply it by atomic mass of hydrogen is 2 and molecular mass of H2O is 18. Now multiply it by 100 and we will get the percentage. I should have minimized the calculator. My bad. 54 divided by 4.24 and that becomes 0.6, I get, and that now 1 divided by 9, 0.1 multiplied by 100, that will become 6, I guess. 0.6 multiplied by 100, So it's 6.67 percentage is hydrogen. Now if this is there is 40%, we calculated, yeah, maybe 40% we calculated, and now the percentage of hydrogen is 6.67. so that means that the remaining is, we can calculate the percentage of oxygen. Percentage of oxygen by subtracting the percentage of hydrogen and carbon from 100. This will give, now we know the percentage of carbon for 100 minus 40 plus 6 is 46.6, that will give 53.4% of oxygen. Now we have to divide it by, we have to form its mole ratio. So we simply divide them by their atomic masses. Now the percentage, we write it by in ratio forms. This is, first write C ratio H ratio to O. The carbon percentage was 40, hydrogen was 6.6, and oxygen was 53.4. Now divided by their atomic masses, 12, 1.008, and then we'll divide by 16. Divided by 12 gives 3.3. 6.6 divided by 1 gives 6.6, that is, and 53.4 divided by 16 gives 3.3 as well. So they are two equal, and this is one is twice that of 3.3. We can cross it. 1, we can write in simpler ratio. So we have determined the empirical formula that of the compound, and that is CH2O of acetic acid. By combustion analysis, we have determined the empirical formula of acetic acid. Now, how to determine the molecular formula? For determining molecular formula, we have to calculate N. What is N? N is just the this is a multiplier that will multiply it with the numerical formula to give off molecular formula. So to determine it, we will write N is equal to molecular mass of acetic acid and molecular mass of CH2O. That is the determined empirical formula. Now the molecular mass of acetic acid, as we know, is 60, and the molecular mass of the compound is if we go SL 12, the atomic mass of carbon is 12 and hydrogen is 2, so it becomes 14, and plus 16, that is what our atomic mass of hydrogen, then become 16 plus 14, that means it's 30. So the n will give out as 2. Now we will multiply this by the empirical formula. We will multiply it by the subscript that are written here. So that will become C2H4 and O2, and this is the molecular formula of acetic acid. You can calculate in BIEK. There is only one way to calculate the empirical formula given, that is through the combustion analysis. Moving forward is the topic which is very easy, that is mole. What is mole? Mole is simply the 6.02 100 to 23 particles of any atom molecule. It's just a mole. Okay, so if I say that there is 1 mole of carbon dioxide, that means I have 6.02 molar 23 particles of carbon dioxide. Now by definition, mole is the number of particles present in 12 gram of carbon 12 atom, and that is equal to 6.02 molar 23. Now how to calculate the mole is a very easy calculation. How to calculate a mole? Like suppose that if I decide to take the example of CO2. I have 28 gram of CO2. I will divide it by the molecular mass of CO2, and that is 12 plus 32 plus 12 is 44. I will divide by 44, and the calculated value will be the mole, and the number of Avogadro number, determined by multiplying it by Avogadro number, that is 6.02. That's 3.83 multiplied by 10 is about 23 particles in 28 gram of .63 moles. In 0.63 moles, there are 3.83 let us 23 number of particles, or simply molecules, the number of molecules. Okay. Now we are moving towards stoichiometry, and also you have to know that if there is any molecule, this is carbon dioxide. Carbon dioxide is not a solid usually. In the form of gas, that's true. But if it's in a gaseous form, we the 1 mole of carbon dioxide, 1 mole of gaseous carbon dioxide will have 22.414 decimeter cube. Means that 1 mole of gaseous carbon dioxide occupies 22.414 decimeter cube. But if there is a solid CO2, we will say 1 mole is 44 grams. Okay, so if you have 22.414 decimeter cube for CO2, that means it's 1 mole. But if there's 44 gram of CO2 solid, that will be 1 mole of CO2. Now moving forward to stoichiometry. Uh, Stoichiometry is simply the calculation of we calculate the mass of product produced, the number of the if a product is formed, I was circuit what is formed, what will the reactants and what will the mass of the reactants and how much number of moles are used. We can calculate that. The stoichiometry, if we apply stoichiometry in daily life, that will be not uh, as correct, exact, as precise as we calculate in book or our calculations, because there is side reaction that occurs. Like for example, if we burn carbon dioxide, there is a sometimes there is not a complete combustion, so CO2 is not formed, but CO is formed, that is carbon monoxide. So the side reaction had occurred, and obviously yield of CO2 is reduced. Now, for the important assumption that we take in stoichiometric calculations, that are the first assumption is that we suppose that all the reactions will convert into product and no side reaction and result. Like CO that doesn't form, but the C plus O directly form to CO2 and no CO2 is formed. That is the assumption we take in solving stoichiometric calculations. Uh, and this is the two assumption that we take. The first is the reactant are completely converted product, no reactant remains. That if we are talking about reversible reaction, we can't get this thing out. So we are talking, we cannot apply stoichiometry on reversible reactions, and no side reaction occurs, means that no CO is formed in case of the formation of carbon dioxide. Now, how we calculate the reactant or products that are involved in the calculation. That is three type of relation, that is mass relationship, mass volume relationship, volume relationship, through which can we calculate it. Now I will do all these things. First we will go into mass relationship. We are taking an example, that is example 2, and I will how to solve it. Now that in this example, it is said that chlorine, the NaCl solution, that is said chlorine is produced in large scale by the electrolysis of NaCl aqueous solution. We have to calculate the mass required to produce 142 gram of chlorine. Okay, now we have to calculate was required to produce 142 gram of chlorine. Now we are doing mass calculation. Now we have first have to write down the equation. Now the equation of electrolysis of NaCl is, noticing the brush, okay, NaCl with H2O give off chlorine gas and sodium hydroxide along with hydrogen gas. These both are liberated at separate electrodes and use this evolution form in the equation. Now we have to balance this equation. There are three hydrogen atoms that can't be possible because we have H2 molecule used. So we are adding H2 and now balancing it. If there is 2 NaOH, there will be a 2 here as well. Cl2 satisfy, H2 satisfy, now the equation is satisfied. Now, how to calculate? So first of all, we have to find out what we are saying, that 142 gram of chlorine is required. Right, we have to find 142 gram of chlorine. Now we have first find out its mole, and 1 mole of chlorine can be find out. The mole of chlorine can be find out by dividing the mass with its molecular mass. Now divided by 71 and it will give 2. So there is 2 number of mole. We have to produce 2 mole of chlorine. Okay, so we have to produce 2 mole of chlorine, and there is 2 H2O and 2 NaCl. Now if we can write now the mole ratio. We have to, how much we have to calculate? NaCl we have to calculate. Now we should write now here NaCl ratio to chlorine. The ratio to NaCl to chlorine is 1:2. That is 2 NaCl is used, that the 2 ratio of NaCl used, 1 ratio of chlorine is produced. So basically if we use 2 mole of NaCl, 1 mole will be produced. So we'll be using 4 mole of NaCl to produce 2 moles of chlorine. Now if we using 4 mole of chlorine, then we can obviously calculate the mass of NaCl. The mass of NaCl will be calculated like this. Mass, as we know, is equal to mole multiplied by molecular mass, that is MMI. That now there is mole is 4 mole is required to produce 2 moles of Cl2. So we multiply 4 multiplied by molecular, the molecular mass of NaCl is 23 plus 35. That will become 58.5. We multiply it by 58.5. I should have learned to minimize the calculator. Okay, now multiply by 4 multiply by 58.5, and that will give 234. So in order to produce 142 gram of chlorine, we need 234 gram of NaCl. This is a very simple calculation. Now we'll move into mass volume relationship, and we'll doing this example given in the book. The example is, I'm writing it down here. We are asked to calculate the volume of oxygen gas. Oxygen is a diatomic molecule. The complete combustion of it of CH2, that is carbon disulfide. Remember that is carbon disulfide. Motion of CH2. Calculate 2 moles of CH2. Calculate volume of CO2 and SO2 produced as well. Now we can write the equation. like this, that is CS2 plus plus 3O2, it gives CO2 plus 2SO2. Now if the mass, we have to know there are 2 moles of actually the CS2. I can write here 2 moles of CS2, and we have to calculate the volume of CO2 and SO2 produced. Now the symbol is that, which is so too simple, that we have CS2, the ratio of CS2 to SO2 is 1:2 in the reactor and product side. So that means if we use 1 mole of CS2, 2 mole of SO2 will be produced. So if I use 2 mole of CS2, 4 moles of SO2 will be produced. So as we know that 1 mole of any gaseous molecule has 22.414 occupies 2.414 decimeter cube of volume. The 4 will occupy 22.414 multiplied by 4. Now 22.414 multiplied by 4, that becomes 89. So 89, the molecule of SO2 is produced 89.6 tm cube. Now to calculate the volume of CO2 produced, to produce the carbon dioxide, we have now to calculate. We also have to calculate the volume of oxygen, that we have now calculated. So calculate the volume of oxygen, we just compare CS2 by O2. So for combustion of 1 mole of CS2, 3 moles of O2 is required. So if we are utilizing 2 moles, we have to go for 6 moles of oxygen molecule. Now multiply 6 to 22.414 multiplied by 6. So 134 decimeter cube is used of oxygen. Now we are left with CO2. Now compare CS2 with CO2, and that ratio is same. So we can say that 2 mole of CS2 will give 2 mole of CO2, and that will be equal to 44.818 decimeter cube. Now we have know all the three. The CO2 produced, the volume of O2 produced will be 134.434 decimeter cube. The volume of CO2 will be 44.818 decimeter cube, and the SO2 is 89.6 decimeter cube. Now moving forward, that is the volume relationship. That is simple as well. Now we are suppose that we are burning hydrogen sulfide in air, as illustrated in this equation. It will give Yeah, this will give it water and SO2 in this according to this equation. Now we have to calculate the volume of O2 required to burn 900 decimeter cube of H2S, and also find the volume of SO2 produced. Now the ratio is given like this: H2S is ratio to O2 is 2:3. So that means if 1 mole of SOS will require 1.5 mole of O2 to combust. Now if we have 900 decimeter cube of that hydrogen sulfide, if we can actually calculate the number of moles of H2S, but we are not doing it. We will just multiply by 1 multiplied by 2.2414, but we are not doing this because we have the given. The given is we have, this is simply the ratio but not the moles, but we can also call it moles because the ratio will be the required will be same. Now the how to burn 900 decimeter of H2S, we will multiply 1.5 to 900. It will give the volume of O2 required to burn H2S. 1350 decimeter cube of O2 is required to burn H2S. Now the volume is calculated now, that is required to burn 900 decimeter of H2S. We are finding the volume of H2. The ratio to H2S and SO2 is same. So actually that if we are there is a 900 decimeter cube of H2S, there will be similar volume of SO2. Now if there is because there is the ratio of product to reactant is 2:2, and that is simply we can simplify it to 1:1. So it's 900 decimeter cube. SO2 will be produced. SO2 produced will be 900 decimeter occupied and 900 decimeter cube of volume. So all these calculations are done. We are left with only last topic of BIEK, that is limiting reagent. What is a limiting reagent? Limiting reagent is that sometimes that actually stops the reaction, that is present in lesser amount, so it's actually stop the reaction. For example, if I have a squash bottle and I have to pour 2 spoons per glass, and I have only 4 glass, and in squash bottle there are a number of 6 spoons left. So the limiting reagent is the squash syrup. Now we can how to calculate it. It's a very simple task. Let's find out. Let's see which are the pieces. Okay, now consider this equation that says Na2S. Yes, this example that says that 2 disodium sulfide react with sodium carbonate with SO2 to produce sodium thiosulfate. Now we have to find the limiting reagent. Now if we suppose that equal masses of 200 equal masses of disodium sulfide and sodium carbonate are to be used, which of the reaction which of the compound will stop the reaction? Now we will compare the number of moles Na2S and with sodium thiosulfate. We have to find out the limiting reagent that will limit the formation of thiosulfate S2O3. The ratio to each other is 1:1 because the 2 moles of Na2 sodium disulfide for 2 moles of sodium thiosulfate. The ratio will be 1:1. Now I have removed that part of the screen because I have wrote the question wrong. 1 mole of Na2S is 2 mole of Na2S producing 3 moles of sodium thiosulfate. So we will write it again here. Now 1 mole will produce 1.5, and the mole produced of we will calculate the mole of Na2S first. To calculate the mole, divide 200 by 78. That is the molecular mass of Na2S. That will give 2.56. That is, now we'll multiply by 1.5 and it will give 3.864 mole. And that means that if we use 2.56 moles, that is 200 grams, 3.84 gram of thiosulfate will be formed. Now we are moving toward sodium carbonate. How much sodium carbonate produce how much moles? The lesser number of moles, that will be the limiting reagent. Now we'll be moving towards sodium carbonate ratio to Na2 S2O3. The ratio in the equation, the ratio to sodium carbonate and thiosulfate is 1:3. That if 1 mole of Na2CO3 is used, 3 moles of thiosulfate will be formed. The number of moles we calculate, the number of moles of Na2CO3 divided by 200 divided by, that is become 46 plus 44 plus 16, that gave 106. Now the number of moles will form will be 1.88. So as will be, the ratio is 3, so we multiply by 3, 8. If we multiply 1.88 by 3, it gives 5.64 moles. Now moving forward, we have to calculate the number of modules by SO2. Now we compare SO2 with thiosulfate. The ratio to SO2 to thiosulfate is 4:3. So 1 mole of thiosulfate will produce 3.14 moles of 1 mole of SO2 will produce 3.4 moles of thiosulfate. Now we'll divide by 200 gram with divided by so 32 plus 32 will become 64. 200 divided by 64 gives 3.125 moles. We'll divide 3.124 multiply by 3 and then we'll divide it by 4. That will give 2.34 moles. So the least number of moles is produced by SO2. So we know that SO2 is actually the emitting reagent, as the number of moles produced by SO2 is lesser than those produced by sodium disulfide and sodium carbonate. Now we are done with BIEK. Moving to the difference between the syllabus of BIEK and federal for the first chapter is just one topic that is more in federal, and that is yield. What is yield? Is just a ratio between theoretical and the yield actually produced during a chemical reaction. Now industrially there is a reaction given, that is when quick limestone is roasted, that is CaCO3. When CaCO3 is roasted, CaO, that is quicklime, and carbon dioxide is produced by this ratio. Now if the actual yield 2.5 kilogram is produced, that is actual yield. This is actual 2.5 kilogram is produced when 4.5 is kilogram of CaCO3 is roasted. Now find out the percentage yield. Now we have to find out the percentage. To find out the percentage yield, we use theoretical yield, that is unknown. Now theoretically is unknown. To calculate it, it's very simple. Use stoichiometry. That we can write CaCO3 ratio to CaO. Quick lime is 1:1. So 1 mole of CaCO3 will provide 1 mole of calcium. Now we'll calculate quick lime. We will first calculate the mole used of. Now, as you know, we find mole from grams, so we convert kilogram to gram. That will become 4,500. We'll divide it by the molecular mass of calcium carbonate. That is 40 plus 12 is become 52. 52 plus 32 plus 16, and that is what is actually I have to add it now. 40 plus 12, 52. 52 plus 32, 52 plus 32, 84. 84 plus 16, that is 100. Now divided by 100, and it will give 45 moles. So 45 moles of calcium carbonate produce 45 moles of quick lime. Now for mass of 45 kilogram of 45 moles of quicklime. 45 molecular mass of quicklime, that is 56. We'll multiply 45 with 56. 45 multiplied 56, which will give 2520 kilogram of what? Limestone. Now we'll quicklime. Now we will have to find out the percentage yield. The formula is simple, as we know that to find out percentage yield, which will be a ratio between the actual yield and theoretical. As we are finding on the percentage, we will multiply it by 100. The theoretical yield is 2520 and actually is 2.5 kg, that is 2500 gram, and we'll multiply by 100. What will be the answer? 25000 divided by 2520. So actually the 99.2 percentage of yield is produced. The less is 0.8 is gone inside reactions. So now if we move towards Akan motion, now we have done we said that the first topic is mole Avogadro number and mole relation to that. We have done that. Number of moles, we have calculated that. Interpret a balanced chemical ratio, and we have done that. Calculate mole ratio based on the conversion factor, we done that. Percentage of mass, we have done that. Deduce molecular and chemical formula, we have done that. Reduce imaging pattern, we have done that. Differentiate between actual yield and theoretical and percentage yield. I can differentiate it easily. The actual yield produced during a reaction is performed in a laboratory or a factory, etc. Theoretical is calculated yield, and percentage yield, the ratio between actual and theoretical yield. The other thing is the significance of consistent quantitative science in daily life is an application based topic, I guess, and so we have to list the significance in quantitative science that we have to calculate, like we can calculate the product form, we can calculate how much reactant can be used, how we can calculate how much volume is required to produce that much volume of everything. We can add the quantitative science based a list of these things we can write about it. Now we can use calculate percentage, that is we have done right now. So we have done with the chapter 1 in all 3 boards. So now I will be posting the another chapter of chemistry or any other subject. I will be posting chemistry, Ohio, and physics, but not even that, and that will be a syllabuses for next time. Goodbye.